So a quick reminder, modular arithmetic is the situation where we deal with integer numbers and operations on integer numbers that results in integers, but we want to deal with this within a finite domain of possible values. So the values of those numbers as an outcome of any operation cannot really go to any integer, like they cannot go to infinity. They are limited. So the output of the operation is always limited. The limitations of the output of the operation is from 0, so any operation will result in an output in the modulus arithmetic, and the output is going to be in the range of 0 up to n minus 1, where n is called the modulus of our arithmetic operation. And the way we produce results that are limited to this domain from 0 to n minus 1 is that we take any value a, any integer value a, and we try to find the remainder of this, of dividing this value by the modulus n. We call this a mod n. N is the modulus, the number that defines the limitations of our domain. Our domain is limited from, the results are limited to be from 0 to n minus 1, okay? So n minus 1 is just the modulus minus 1, okay? And the way we map anything to this domain is by taking the remainder of dividing any value by n, okay? So a mod n would mean this is equivalent to the remainder of a divided by n. So the remainder of the operation of dividing a by n, okay? Examples, if I try to represent 11 mod 7, then I divide 11 by 7 and I look for the remainder. The division here will give me a quotient of 1 and a remainder of 4. Okay. Another example, which is very important, since we want to limit our remainder to be only on the positive side, okay? So if we have minus 11 mod 7, the result of the division here is going to give me a quotient of minus 2, not minus 1. Okay? Why? Because if I make it minus 1, then the result of multiplying minus 1 by 7 is going to be negative 7. Negative 7 is actually larger than minus 11, right? Remember, we always try to find a quotient which is, when multiplied by the divisor, will give me some result smaller than the original divided number, right? So here, if we pick our quotient as minus 1, in this case, if we pick the quotient to be minus 1, so minus 1 times 7 is minus 7, but minus 7 is actually greater than minus 11. We want to find something which is smaller than the divided number. The divided number here is minus 11. So in this case, we take a quotient of minus 2. Minus 2 times 7 will give me minus 14. Minus 14 is actually smaller than minus 11. And the difference between those two numbers is minus 11 minus minus 14, which is equal to 3. That's the remainder, right? How do we find the remainder? Remember the division algorithm? The division algorithm says what? Any number a, when divided by b, the result of this division is going to be some integer n, q, we call it, the quotient, multiplied by b, plus some remainder. If you want to find the remainder, how do you find the remainder? Okay, r is simply equal to a minus qn, right? And that's what we did here. We were trying to find the remainder, so we said a minus qn, right? Okay, and that will give me a remainder of 3. Okay, so the remainder in this case, so since 3 is the remainder, this is how we represent minus 11 in the modulus of 7. Okay? Similarly, the remainder of dividing 11 by 7 is going to be 4, and this remainder is actually how we represent the number 11 modulus 7 to the finite domain limited by values from 0 to 6. Okay? Any questions so far about the meaning of modular arithmetic? Clear? Now, under that modular arithmetic, we redefine the equal operator with something called the congruence operator. Okay? So two numbers, okay, let's say for example, we are working on mod 3. Okay? So two numbers, mod 3, are congruent to each other if A mod three equals B mod 3. Example, I can pick, for example, 11, right? And I can pick here something like 5. Okay, so 11 mod 3 is equal to what? What's the remainder of dividing 11 by 3? 11 mod remainder 2. Yeah, مش الريزلت remainder 11 mod 3. So this is equal to 2. If you divide 11 by 3, the result is 3. 3 times 3 will give you 9, and the remainder is 2. صح؟ باقي اسمة 11 على 3. If I divide 11 by 3, what's going to be the remainder of this division? 2. Clear ولا مش clear؟ في حد مش فاهم ليه هي 2؟ اللي مش فاهم يسأل يا جماعة. It's better to ask now, because we will build on this a lot. So if there is something not clear at this stage, just ask. ماشي اعمليها بقى حسب, but you need to understand it, because sometimes you need to solve symbolic stuff. If you need to, later on we will solve some equations with symbolic stuff. That's not gonna be doable بالcalculator, مش هتبقى أرقام. طيب. By definition, if we say a number A mod كل مرة اكتب المود ناقصة او mod B or mod N خلينا تمام. This is by definition معناها remainder of A over N. طيب example. Okay. الاكزامبل اللي احنا بنتكلم عليه هنا 11 mod 3. This is equal to the remainder of dividing 11 by 3. When I divide 11 by 3, what do I get? 11 is equal to 3 times 3 plus 2. صح? So the quotient of the division is 3. The remainder of the division is 2. So this is the remainder. Then this means that 11 mod 3, اللي هي remainder of dividing 11 by 3, is equal to 2. Remainder of the division. تمام? Clear to everyone now? Okay? So, if two numbers are equal to each other mod n, we call those two numbers congruent to each other. We don't just say equal. We say congruent to each other. Like this. And the congruence operation is represented by 3 lines, 3 horizontal lines instead of 2 في حالة equality. تمام? This means what? This means that the remainder of dividing A by N is equal to the remainder of dividing B by N. But not necessarily in A or B are equal to each other. It's not true. They don't have to be equal to each other. It's only that when I divide each one of them by the modulus N, they give me the same remainder. But they can be totally two different numbers. Okay? وضحت كده? It's clear what's meant by the congruence. The congruence is equality mod n, and it means that those two numbers, تمام? When you divide them by n, they give you the same remainder of division. يرجعوا لك نفس الباقي. Example here, 11 divided by 3, 11 mod 3, the remainder is 2. So 11 mod 3 is equal to 2. And 5 mod 3, also 5 mod 3 will give you a remainder of 2. So we can say that 11 and 5 are congruent to each other. We can write here that 11 is congruent to 5 mod 3. Congruence always happens mod something. We cannot say two numbers are congruent to each other and just keep it like this, right? We have to say mod what? What's the modulus? Okay? Because if we are dealing with, for example, mod 4, probably 11 and 5 are not equal to each other. They are not congruent to each other mod 4. Because the remainder of dividing 11 by 4 is going to be what? 3. The remainder of dividing 5 by 4 is going to be 1, right? So they are not congruent to each other, mod 4, for example, right? So always for the modulus, for the congruence, we have to specify the modulus value. Otherwise, the relation is not complete, and it doesn't make sense. Any questions? Okay. Now, if two numbers are congruent to each other, we have defined what does this mean. Based on this definition, a number is congruent to 0 mod n only if n divides that number. صح? Because again, it means this statement means that the remainder of dividing this number by n is equal to 0. Okay? And if the remainder of dividing a by n is equal to 0, this is the same meaning as n divides a. صح? n is a divisor of a. So this relation is exactly equivalent when we say any number, like for example, 9 is congruent to 0 mod 3. Because when we divide 9 by 3, we get a remainder of 0. And of course, when you divide 0 by 3, you get a remainder of 0. 0 divided by anything will give you a remainder of 0. Because 0 is can be divided by any number except 0. Okay? So when we say that, this statement, when we say that a number is congruent 0 mod n, this implicitly and clearly imply that n is a divisor of a. n divides a. Here are some important relations or congruences. Okay? If a is congruent to b mod n, if a is congruent to b mod n, then this means that n will divide the difference between a and b. It's by intuition كده, this relation is correct, but then it shows you down here why this relation is always correct. So again, if a and b are two congruent to each other, mod n, this means that n will be a divisor of the difference between those two numbers. تمام? Let's take our example that we looked at before. 11 mod n. So we said that 5 is congruent to 11 mod n. تمام? Mod, it's not mod n, mod 3. Okay? We mentioned that in the previous slide, right? So this immediately means that 11 minus 5 can be divided by 3. Right? This is true or not? 11 minus 5 is equal to 6. And 6 is a number that can be divided by 3. So 3 is a divisor of the difference. This is what we say here. If a is congruent to b mod n, then n is a divisor of the difference between those two numbers. Okay? That's first relation. Second relation, if a is congruent to b, it's the same as saying b is congruent to a. So 5 is congruent to 11 is the same as 11 is congruent to 5. There is no difference in terms of flipping which one comes to the left side of the congruence operation and which one comes to the right side. It's the same. It's similar to saying if a is equal to b, then b is equal to a. That's the same when you say for regular arithmetic. Here, if a is congruent to b, then b is congruent to a as well, for the same modulus, mod n. Don't forget that for congruence, you have to specify the modulus. Tamam? Another one is kind of like the cascading of congruence. So if a is congruent to b mod n, and b is congruent to c mod n, then this implies that a is congruent to c. A is congruent to c mod n. Tamam? Similarly, if I say, for example, that 11 is congruent to 5 mod 3, and 5 is congruent to 2 mod 3. These two relations are correct, right? 11 divided by 3 will give me a remainder of 2. 5 divided by 3 will give me a remainder of 2. Similarly here, 5 divided by 3 will give me a remainder of 2. 2 divided by 3 will give me a remainder of 2. So these two are congruent. These two are congruent. Then definitely 11 is also congruent to 2 mod 3. Okay, that's this relation. Tamam? Here it gives you some examples of those relations that we have done. Okay. I leave the numeric examples for you to kind of visit them quickly. They don't have much details. And the part above explains to you why this is always true. Also very simple to follow. Some other important properties of congruences in terms of operations. If you have A mod n and B mod n, and you add those two numbers together, and then you take the result, mod n again, this is exactly similar to not doing this, just simply adding A to B, and then taking the result mod n. Okay? So whether you represent each one of them with a modulus of n, and then you add them together, and then you take the result modulus n, or you just leave each one of them as is, without doing any representation, adding them together and then taking the result mod n, those two operations will give you exactly the same result. So basically, no need to do this in the middle. Okay? We can just simply add A to B without really doing the modulus operation in the middle. Okay? And the next slide will show a few numeric examples on this. Similarly, the same thing when you do subtraction. So A mod n minus B mod n, and then taking the whole result mod n, is the same as just simply subtracting B from A and then taking the result mod n. Will just give you exactly the same. For multiplication also, it's the same thing. If you multiply two numbers, first by taking the mod n of each one and then multiplying and then taking the result mod n, or just simply multiplying them and taking the result mod n, it will give you exactly the same result. Here it tries to explain why. Just read it for your information, but it doesn't really, it's not a requirement in terms of proving or anything. And here it gives you some examples of this. So for example, the addition part, okay? If you take 11 mod 8, so now we are doing everything mod 8. So if I take the number 11 mod 8, that will give me 3, because 11 mod 8, the remainder of dividing 11 by 8 is equal to 3. And if I take the number 15 mod 8, this will give me 7, because the remainder of dividing 15 by 8 is gonna be 7. And then I add those two. This is simply A mod n plus B mod n, right? This is this, which is 3. And this is this, which will give me 7 in this example. So if I add 3 plus 7, and then do the whole thing mod 8 again, this is equal to what? 10 mod 8. What's 10 mod 8? 2. The remainder of dividing 10 by 8 is 2, right? Now, if I don't do this, I just simply add 11 and 15 without modding them. So just add this to this without really doing the mod here. 11 plus 15 is what? 26. 26, and then take this mod 8. What's 26 mod 8? 2. So exactly the same that we got when we did the modding on each one of them and then added those and then did the modding again to 8. Okay? So this verifies the property that we looked at before. That if you do this, it's exactly the same as A plus B first. Just add the numbers as is and then take the modulus to 8 or to n. Okay, that's what we did in this step. And it gave us the same result as this step. Okay? Same, you can, again, another example here for subtraction, another example for multiplication, trivial ones, so you can go through them. I just wanted to do one numeric example with you, so you can see those symbolic terms, how they look like in actual implementation or actual calculation. خلاص? Any questions? Everyone is happy? Okay, here we see the summation of, so arithmetic operations, modulo 8, the summation of any two values mod 8. So 0 plus 0, the result is 0. 0 mod 8 is 0. 1 plus 0 is 1. 1 mod 8 is 1. 2, 3, and for example, let's say 4 plus 5. Okay, mod 8. 4 plus 5 is 9, right? 9 mod 8 is 1. So we can say that 4 plus 5 mod 8 is equal to 1. Okay? Let's take another example. 6 plus 6. 6 plus 6 is actually 12. But then 12 mod 8 is equal to 4. Why? Because 12 divided by 8 will give you a remainder of 4. So we can say that 6 plus 6 mod 8 is actually equal to 4. Okay, so this table shows you the addition of any two numbers modulo 8. Of course, it has only to go up to 7, because beyond that, you will go back to 0. There is no 8, 9, 10, because we are working modulus 8, right? So the available set of numbers for us are from 0 to 7 only. Okay? Similarly, this table shows you multiplication of any two numbers modulo 8, right? So, for example, let's take 4 times 5. So 4 times 5 is 20. 20 modulus 8 is equal to 4, right? Because the remainder of dividing 20 by 8 is equal to 4. So let's see, 4 and 5 multiplication mod 8 will give us 4. And similarly, you can get all the other results in this table. Okay? طيب. This is very interesting and very important. Remember, in regular arithmetic, there is always something called the additive inverse and the multiplicative inverse. تمام? Additive inverse is defined as, in regular arithmetics, we say A plus B. If it gives me 0, then B is the additive inverse of A. تمام? And the multiplicative, we say that A times C is equal to 1. This means that C is the multiplicative inverse of A. So this is the additive inverse. When added to A will give you 0. The multiplicative inverse when multiplied by A will give you 1. تمام? Okay. Let's see what happens in modular arithmetics. And particularly, let's take an example. It's easier to understand with an example. Let's take an example again of modulo 8. So this table is for modulo 8. The first column shows me the numbers from 0 to 7. Second column shows me the additive inverse of that number. Okay? The value that when added to that number will give me, additive means when added to this modulo 8 will give me 0. Right? That's the definition of additive inverse. It's a number when added to the original number A will give you a 0. So we can see here, 7, this is positive, not negative, right? Because our allowed values are positive in modulo arithmetics, right? But we can see that if I add 7 to 1, what do I get? Modulo 8. 7 plus 1 is 8. 8 modulo 8 is what? 0, right? So we say that 7 is the additive inverse of 1. Let's add 6 to 2, right? 6 added to 2 will give me 8. 8 modulo 8 is 0 because there is no remainder. صح? And then 6 is the additive inverse of 2. Similarly, 5 and 3. If you add 5 to 3, it will give you 8, which means 0 as a result, modulo 8. Interestingly, 4 is the additive inverse of itself. If you add 4 to 4, it will give you 8, and that would mean 0 modulo 8, right? And so on. So this shows you the additive inverse of the numbers here, right? Which are the numbers when added to this, the result modulo 8 will give you 0. For the multiplicative inverse, it's very interesting. Not all the numbers, not necessarily that all the numbers modulo 8, for example, will have a multiplicative inverse. What's the definition of a multiplicative inverse? It's a number when multiplied by the original 1, and then you calculate the result. Modulo 8 should give you 1. In the case of 1, when you multiply 1 by 1, and then you take that modulo 8, it will give you a remainder of 1. So this means that 1 is a multiplicative inverse of itself. What about 2? If we try to do this for 2, we will try all the possible numbers and we'll find none of them will give us an output of 1 modulo 8. So if you multiply 2 by 0, تمام, the result is 0. 0 modulo 8 is equal to 0. So definitely 0 is not a multiplicative inverse of 2. Let's multiply 1 by 2. 1 by 2 is equal to 2. 2 modulo 8 is 2. It's not 1. So that's not a multiplicative inverse. 3. 3 times 2 is 6, right? 6 modulo 8 means 6. So it's not 1. So again, 3 is not a multiplicative inverse. 4 times 2 equals 8. Modulo 8 will give me 0. So 4 is not a multiplicative inverse. 5 times 2 is 10. 10 modulo 8 is 2. So again, not 1, right? So this means that 5 is not a multiplicative. 6 give you 12. 12 is 4 modulo 8. 7 will give you 14. 14 is 6 modulo 8, right? So I'm done. Run out of all the numbers from 0 to 7. None of them, when multiplied by 2, will give me 1 as a result modulo n. This means that none of the numbers is an inverse, is a multiplicative inverse for 2. So we don't have a multiplicative inverse for 2. If we try this for 3, we will find that 3 times 3 will give us 9. 9 modulo 8 is equal to 1. So this means 3 is an inverse of itself. 5 is an inverse of itself. 7 is an inverse of itself. Just as a caution, it's not true that for any modulo arithmetic you will have the number as the inverse to itself. It just happens that this is the case for modulo 8. But if you try modulo some other numbers, you will find here 2 different values when multiplied together will give you a 1 modulo whatever, right? And you will find maybe different, in some cases there are always an inverse, in some cases some have inverses and some don't, and so on, okay? The key idea is to understand the definition of multiplicative inverse and the definition of additive inverse, and to be able to figure them out, to be able to find what's the multiplicative and what's the additive, and to understand that there is always an additive inverse for any number, modulo anything, right? But sometimes there are multiplicative inverses and sometimes not. So it's not necessarily that for every number modulo n, there is a multiplicative inverse. But there is always an additive inverse, okay? Any questions? This is another set of important properties of operations, which is again happens in most of the arithmetic operations that you study in any domain. So if you add 2 numbers, w plus x mod n, it's the same as like flipping the order, right? We call this the commutative property. Similarly, if you multiply w plus x, it's the same as multiplying x times w modulo n. That's the commutative for addition and multiplication. Associative means that if you do 3 operations, you start by doing 2 of them first and then the third one. It's the same as doing 1 and then 2 later. So by combining those first and then adding it to it, it's the same as combining those first and then adding this to it, okay? This is for addition and multiplication again, called associative property. Distributive, it combines multiplication and addition, so w times x plus y mod n is the same as w times x plus w times y, and then the whole thing mod n. Okay. That's called the distributive property. The identities, there are 2 identities, one for addition, one for multiplication. 0 added to any number mod n is the same as the number itself mod n. That's an identity for addition. 1 times any number mod n is the same number mod n. This is the identity for multiplication. Additive inverse always exists. Multiplicative is not listed here because it can exist, it might not exist. It's not always true that you will have a multiplicative inverse for any number mod n, okay? But it's true that you will always find an additive inverse for any number mod n, okay? Going back to, remember when we studied the Euclidean algorithm, and I asked, I didn't, but you can think of the algorithm that we studied before, and it just shows you that programming-wise, you can think of the Euclidean algorithm as a recursive operation. I don't know if you have studied in programming a recursive operation. A recursive operation is when you have a particular logical operation or calculation operation such that you can represent that by a function that calls itself from inside. So you see here, if I'm trying to use the Euclidean algorithm with two numbers A and B, remember what was happening. If B is equal to 0, then the algorithm finishes and A is the result that we are trying to get, the greatest common divisor, right? If not the case, what do? We actually do the same thing, call this function again, but just simply, which was for example GCD, right? But just simply changing the values that goes into the function. So we change B to be in the place of A, and we put in the place of B the remainder of dividing A over B, right? That's what we did in the Euclidean algorithm. You remember how it works? Okay. So again, if you think how this is going to be executed, as long as this does not reach 0, right? We will call the same function again, but swap the values. And then inside that, when you are calculating this, it will check. Do I have 0 here? No. Then it will call itself again, one more level in the stack of calling functions, but the values are going to be A mod B will be here, and B divided by A mod B with the remainder will be on this side. And it will keep doing this until at some point it reaches that this value is equal to 0. In that case, it will just return this value to the call. Okay, that's called a recursive function, a function that calls itself over and over again until it reaches the end of the calculation. At that point, it returns the value. No need to really write a complicated program. It's just a function that calls itself. Every time it changes just the value that's being passed to the function. Okay? That just, again, this is just a programming idea. Nothing really theoretically important in this case. Right? The more important part is, remember, the Euclidean algorithm was trying to find the greatest common divisor of any two numbers, A and B, given to the algorithm, by doing successive reduction, right? So you reduce them to smaller numbers, smaller numbers, smaller numbers, until you reach that one of them is 0, the other one becomes that greatest common divisor that you are trying to find for A and B. That's what the standard Euclidean was doing. In addition to that, we can do one more thing, right? Which is finding a representation of this greatest common divisor. So in addition to finding the GCD, we also try to represent this as a linear combination of the two numbers A and B. So we are finding the greatest common divisor of A and B. That's the regular or the standard Euclidean that we learned last time. And then the extended is also adding one more step to try to represent this greatest common divisor as a linear combination of those two numbers A and B. Why we need this? This is useful actually in cryptography, particularly the RSA encryption that we will touch upon in the coming lectures, inshallah. Okay? So in addition, so the extended Euclidean algorithm, number one, it finds the greatest common divisor of two numbers. Number two, it represents this greatest common divisor as a linear combination of those two numbers A and B. Okay? And let's see how it does this simply, and the explanation is going to happen through a numeric example, because if I try to explain it using equation, it will be really confusing. I have a slide that represents that using equation, but I think it's much easier to go through it with an example. Okay? But just to give you an idea how it works. Remember when we were trying to do this, we used to kind of go through equations. So we have A and B, we want to find the greatest common divisor, then we represent A using the division algorithm in terms of B to get the remainder, right? And then we take that remainder, it becomes our new B, and the previous B becomes the A, and so on, right? So we did several equations when we did the example for that. Now to find the second step, we'll actually go through these equations backwards. And I will show you what I mean by this, okay? So here, this is a good example of how to do the extended Euclidean algorithm. First step is just to find the greatest common divisor, and we are talking here about the two numbers, 56 and 15. By just looking at this, you can figure out quickly that 56 and 15 do not have any common divisor, except one, of course. One is a common divisor of any two numbers, right? But again, imagine that they were like large and we were not able to figure out that. So we have to go through the Euclidean algorithm. What was the Euclidean algorithm doing? First step was to represent 56 in terms of 15 and then get the remainder, right? So we know that 56 is equal to 3 times 15 and the remainder is 11. Next step, instead of being like looking for the greatest common divisor of 56 and 15, now we use 15 and 11. So 15 is equal to 11 multiplied by some value plus another remainder, 4. That's what the greatest common divisor Euclidean algorithm was doing, right? Then in the next step, it tries to use those two and find the new remainder. So 11 as a function of 4, and the remainder is 3. The next step, we deal with 4 and 3. So 4 is equal to 3 times 1 plus a remainder equal to 1. And then last step, we reach a remainder equal to 0. So we know that what we need to return is this, or like the last B, or the current A. The same thing, okay? Then our greatest common divisor is this number. Now we go and plug everything back. So we start from this equation, which is supposed to be the last one, and we take its B directly as our result of the greatest common divisor, right? And then we say that the 1 can be represented in terms of 3 and 4. 1 is equal to 4 minus 3 times 1, directly from this equation, right? And then we substitute the 3, which was the remainder here in the previous equation, by the other two factors, right? So 1 is equal to 4 minus 3 times 1. The 3 is 11 minus 4 times 2 from this equation, right? The 3 is 11 minus 4 times 2. I can take this to the other side. So I replace this 3 by 11 minus 4 times 2, right? And then just simplify this, and while simplifying, keep it as 4 and 11, because those are the two parameters that you care about. So it's eventually this becomes 4 times 3, because we have here minus 4 times 2, and we have also another 4 outside here, right? So minus minus becomes plus, and it's 4 multiplied by 3, and then we have only 11 as one factor, okay? Go again and try to substitute for the 3, similar to what we did here. Substitute for the 4, similar to what we did here when we were substituting for the 3, okay? So substitute for the 4. If you want to substitute for the 4 was the remainder in this equation, so you can substitute using this equation, okay? So again, we substitute in place of this 4, or the one that we see here in the simplified version, the 15 minus 11 times 1. We remove the 4, and we replace it by 15 times minus 11 times 1, right, here. Multiplied by 3, right, minus 11. Again, gather the terms together. You will end up with terms with respect to 15 and terms with respect to 11, right, which comes in this equation, okay? And one more time, you substitute for the 11, because it's the remainder on the previous equation. You substitute from this equation, and the end result is going to be 1 is equal to 15 times 3 minus 56 minus 15 times 3. That's the substitution from this equation for the 11, right? For this 11 times 4, okay? And if you simplify this, it becomes 15 times 15 minus 56 times 4. That's what we were looking for. We were looking for 1 as a function of the 15, the B, and the 56, the A. So that's the integer multiplied by B, and this is the integer, the minus 4, multiplied by A. So I can say that 1 is equal to 15 times 15 and minus 56 times 4. So the X and the Y that we were looking for are the minus 4 and the 15. Okay? You got the idea? How to use those equations to backward substitute until you reach the one represented as a linear combination of A and B. Here is our A. We're trying to find the greatest common divisor of A and B, 56 and 15. We found that the greatest common divisor is 1, and then through back substitution, through these equations, every time we try to substitute the remainder of the equation by the other two terms. And the remainder of the equation will appear on the equation that we have here, okay? So every time we are trying to substitute for the remainder. 1 is equal to 4 minus 3 times 1. 3 is equal to 11 minus 4 times 2. 4, the remainder, is equal to 15 minus 11 times 1. 11 is equal to 56 minus 15 times 3. That's the substitution that we have been trying to do here. Substitute for the 3, substitute for the 4, substitute for the 11. Okay? And go backward, you will end up with the greatest common divisor, the 1 that you got here, represented as a linear combination of the two numbers, the 15 and the 56. The linear combination here is minus 4 times 56 and plus 15 times 15. Okay? So we have reached the objective, yes?
In the second step where you substitute for 3, why are you multiplying it by 1 again? Like
From here? What do you mean by
like
1? Here?
For 3, it's just 11 minus 4 times 2.
Yes.
So why is it like?
Because it's here 3 times 1. So we remove this 3 and we replace it by 11 minus 4 times 2.
Oh,
Yeah, I'm just trying to show you that where we did the substitution, right? So that you can track this back to this equation,
oh.
okay? And then again, that multiplication by 1 comes from here, okay? And then, now we gather the terms for the 4 and the 11, okay? Any other questions? This table is in the book. You cannot see it here that much. I'm just putting it here to point you out that it is in the book. And it tries to explain what I explained in the previous slide using equations. So here it shows you the equations of finding the greatest common divisor. So the remainder every time, remainder 1, remainder 2, until you reach the point where you have no remainder, and in this case, this is the output of the greatest common divisor, right? But in addition to that, okay, it shows you here how to calculate the x and the y, the two coefficients of the a and b, where you want to represent d with, okay? But following it from the equations is quite difficult. That's why I didn't try to use this table to explain how the algorithm works. Using it numerically gives you a clear idea how it works, at least much better and much easier to follow, as opposed to going through equations and substituting and saying this coefficient comes from here and this comes from there. It's going to be confusing. But it's there for your reference, okay? I just show it here so that you know you can look it up in the book, and it's there for your reference. I don't advise you to investigate it that much. It's going to confuse you again, but try. If you like to get into mathematical substitutions with symbols, go ahead, okay? Here is an example also, just numeric example, and it shows you things in a tabular format, trying to find the greatest common divisor of 1,759 and 550, going through the Euclidean algorithm, and while doing that, you find the coefficients of the x and y. The final result is going to be that this is the x and y, the coefficients of the a and b, right, that are used to represent your greatest common divisor. Again, just might not be as easy to follow as opposed to the example that I give numerically clearly in steps, but it's there also for your reference. We are done. Any questions? Okay. I just wanted to make sure we push the remaining part of these slides, and then next time, inshallah.